So in the last video, we were able to complete this Walsh diagram and predict, right, where each sort of molecular orbital would go when we bend down from a linear geometry, right? We could predict using those three rules and making sure to watch for mixing effects, whether or not the MOs upon bending would go up or down in energy. So we got this correlation diagram. So now what we're ready to do is we're ready to make predictions about structures. And so we're going to populate each side of the Walsh diagram with electrons. And higher energy orbitals will always give rise to a larger change in energies when moving across diagrams. We're moving across the diagram. And this is where I talked about briefly in the beginning of the chapter how a large LUMO to HOMO gap will give rise to a stable, more stable molecule. And the reason for this is, whatever your HOMO and your LUMO are, those are essentially the energy levels that are going to matter the most, because your other molecular orbitals that are populated, let's say, the molecular orbital below your HOMO, that molecular orbital is pretty stable in energy. So, relatively speaking, on both sides of the Walsh diagram, you're going to have a pretty stable states there, and they're going to be more core-like, so they're not going to be as different in energy. And this is just because bonding in main group compounds is pretty strong. Okay, so this fact is true for main group elements. When we get to transition metal chemistry, we can't make this prediction. We can't just look at the highest occupied molecular orbital and make a prediction about the overall stability of the molecule. We have to consider multiple molecular orbitals. But this is a good prediction and a good approximation for main group compounds. All right, so now we're ready. So here are the different structures some different structures we can look at. And so we have various structures ranging from 2 to 10 valence electrons, and of course, water is in there. So we're going to start out with sort of a weird one, which is this lithium hydride cation. And so this only has 2 valence electrons. How would that work? Well, hydrogen has 1 valence electron. The other hydrogen has 1 valence electron. Lithium has 1 valence electron, right? 1 in the 2s. But now we've removed an electron because it's a cation, so it's total 3 minus the 1 from removing it, so it gets us 2. All right, so we're just going to put our 2 electrons in on both of these, and what happens? We get the following correlation diagram, and it's telling us, well, what's the HOMO? Well, there's only 1 energy. The whole energy of the system is just dictated by this 1A1, but really all we care about is a HOMO, as I talked about. And so we're predicting that this is going to be bent, okay? And in fact, this is bent. It's so bent that we would call it triangular. And we can talk about this. You can only get this molecule in the gas phase to be stable, but that's pretty interesting. So this is matching our prediction, and I just want to take a little bit of an aside here to think about the structure of this. Okay, so how would we draw the structure of this? We have lithium, right? We have lithium, and we have hydrogens here. Okay, and so fine, it's a cation. And so this is sort of naturally how you would draw it, right? But how do you draw this? And this will get into why I wrote triangular, okay? This is, I'm trying to draw a Lewis structure, right? Come on, man, I'm just trying to draw a Lewis structure. Well, okay, you have 2 electrons in this bond. You have 2 electrons in this bond. That's 4 electrons right there. Okay, let's go to our VSEPR, nomenclature and our way that we learned how to do steric numbers and all that, right? So we would say, okay, we have 1 electron for central atom, which is lithium. And then we have two 1-electron ligands. So we get -2 times 1, right? There's 2 of them and there's 1. And then -1 for the charge. And so that's going to be 1 minus 2 minus 1. That equals -2. Divide that by 2. That gets me -1 lone pairs, right? So we have an electron deficient molecule, what I'm trying to say. VSEPR theory can't handle this. It just doesn't make sense, right? This Lewis structure we drew, you can't really draw a Lewis structure for this. It doesn't make sense, right? The Lewis structure formalism doesn't make sense with an electron deficient molecule like this. And so, you know, a more accurate way of thinking about this is something like this, right? Where really you have something like that, okay? And so, you know, let's look at what is the actual molecular orbital that's tying it together. It's these s orbitals. And so, you know, really you have some electron density map that sort of just looks like a big sphere. And it's 2 electrons equally distributed between all 3 bonds, okay? So, you know, maybe you could say there's a 2/3 bond there, a 2/3 bond there, and a 2/3 bond there, or 1/3, sorry. 1/3 bond everywhere, right? 1/3 bond everywhere. And overall you have 1 bond worth because you have 2 electrons tying it together. So this is, you know, just kind of going to show you even further that there are a lot of cases of molecules where Lewis structure and the whole concept of VSEPR just doesn't even make sense. One last thing about this molecule, just because I think it's interesting, is really, you know, the way you can think about this is you have hydrogen gas coming together and it's sort of making an adduct here, okay? And that's another way of thinking that. The lithium atoms associating with a hydrogen gas molecule. But again, me drawing all these lines like this doesn't really make a lot of sense because I have too many electrons accounted for. All right, so there's a little bit of an aside on this interesting electron deficient molecule, but we'll go in the next video and do these other cases.